Hello, my lovely warriors. Welcome to the Nurture series, and you're watching the chapter of the heat transfer, and this is lecture number 2. In lecture 1, we had completed conduction, and today it's time that we do radiation. So, welcome aboard for all the lovely, amazing Capto Shreyas warriors, my army. Welcome aboard, and today we are going to see what exactly is radiation, how do we feel heat from sources, from objects which are far away from us, even though there is no medium present. Look at this bonfire, look at the sun. They are really interesting phenomena, and they all happen at very microscopic level, but we are going to study the macroscopic properties in today's class. And I'm not sure if you know this, but the way bulbs glow is completely based on the phenomena of radiation. Yes, you heard it right. So what are we going to study in today's class? The radiation and its properties, the coefficients of absorption, reflection and transmission, black body emission and its emissivity, Kirchhoff's law and Wien's displacement law, very important ones, and of course Stephen's law and the Newton's law of cooling. Yes, you have Newton here too. So all of this with me, your favorite, your captain, your master teacher, your guide, your navigator on this channel, and I hope you have already attended and seen the quiz which I posted on Instagram. If you have seen that, please put up a thumbs up in the chat box. And yep, before we go ahead, do not forget to hit the like button and hit the subscribe button so that you get all my classes on YouTube for free of cost for 11th, for 12th, for droppers. And if you are younger, then even better, go ahead, join these classes. Alright, Kamal Raj is all set to be radiated. Very good. Hi Gautam, hello Saja, hello Srivatsan. Lecture 1 link is just there behind Srivatsan rather. Just go to videos tab and you will be able to see it. It was just conducted day before yesterday, okay? Still, if you cannot find it, do let me know. Ankit has posted the answer. Wow, very good. Aisha, welcome. Thank you for the heart. Welcome. And Saja is loving the black screen too. EGL, hold on bacha, I have not got time to reply to all the comments, but I'll definitely reply very soon. Yep, so let's get going to the session, and the PDF of the entire session is going to be henceforth only available in the Telegram channel. So let me remind all the lovely warriors, join the Telegram. If you have not yet installed the app of Telegram, please join it, because you will get updates, notifications, important PDFs, homework solutions, everything on the Telegram channel with my handwritten notes, obviously. Alright, hello Tamil, hello Tarare, good evening. Yep, yes, oh Shivram, did I? Oh, I did like your comment on your message on Insta. Thank you. Wow, interesting to see you back here. Also, let me remind you guys, there is a very exciting offer which is going to go on, and that's going to start day after tomorrow. Secret reveal for all of you. The Republic Day offer will start. Yes, that's on Monday. So as soon as Monday begins, you are going to see the Republic Day offer, and that's basically 50% off on all our courses. So a typical course which costed 1,350 after using my discount coupon also, now that will come down to 750 rupees. So that's going to start on Monday, and crash courses will be available at 8,000 rupees for the 12th standard students. So go ahead, check out the link in the description box, because all the toppers, all the students who cracked JEE Mains from Vedantu have taken rigorous preparation via our mock tests, via our test series, our assignments, guided by our master teachers, mentors who have been training kids for a very long time. So go ahead, check out the link, and all that lectures, all those assignments, PDFs will be at your fingertips. You don't even have to travel anywhere. That's the best part about it. So imagine, instead of 9,000, you're going to pay 8,000 from Monday. So that's a secret thing which I'm telling you, so that you can probably hold on, wait and join the course on Monday itself. Here's the first question coming up on your screen right in front of you. A bucket full of hot water cools from 75 to 70 in time t1, 70 to 65 in time t2, and 65 to 60 in time t3. What is your guess? What are these times going to be? Think about it. Thank you, Shivram Ronti. All right, Gitanjali, I'm very good. I hope you two are doing fine. Hi, Dakshin. Looks like you're on time today. Gautam, I would be really happy if you join the long-term batch. So if you're in 11th, join the 11th standard course, which says JEE 2023. Okay, so basically you will get the entire 11th revision, and as soon as my 12th standard batch starts, the long-term batch, you will be enrolled in that. All right, so that's how it goes. All right, so will 1 year V Pro subscription have 11th revision? Yes, Abhinav Mishra, it will have the 11th revision as well. 11th revision, 11 test series, everything is included. 11th standard PDFs, assignments, homework questions, everything will be given to you for all the chapters. So yes, it is there. I'm very good, Munir Nawab. Okay, Tarade saying A, Kalyani saying A, okay, Ankit saying A, Dakshin saying A, interesting. Okay, Vishal, hello, welcome. Oh, Ankit, you are a JEE 2024 aspirant, you are very young, so welcome aboard, and I'm pretty sure you are going to have a head start attending all these classes over here. Well, guess what, the answer is not A, it is actually C. Oops, you guys are wrong, only Kamal Raj, Vijay Kumar was right over there. Yes, Vaishal FF, your chat is visible, bacha. See, that's why you're going to study radiation today. You guys thought that this hot bucket from 75 to 75 degrees Celsius change, it takes T1. 70 to 65, 5 degrees Celsius change, same time. And then 65 to 60, 5 degrees Celsius, same time. No, that's not what's going to happen. It's going to take different amounts of time. And that's what we're going to see. And this question's answer you will understand by the end of today's class. So stay tuned till the end, because the answer to this question will come only after you understand Newton's law of cooling. So let's talk about, yes Ankit, don't worry, you're going to get to know about it. Why is it C? It's not the same, it's going to be different. So first let's start with radiation. What is radiation? See, molecules of solid, liquid, gas, at any given temperature, they have vibration, they have translation, they have rotation, so many degrees of freedom, so many energies are there. When these molecules hit each other, and then when they collide with each other, and they rub against each other, and they oscillate, they accelerate, you will see the charges will accelerate, you will see the electrons getting knocked out, and because of this, when electrons get knocked out, charges accelerate. Every time you will see that there will be photons which will be emitted. Photons, yes. Recollect from side of chemistry, from the subject of chemistry, when electrons get knocked out and the electrons come back, what happens? Photons are emitted, right? You would have studied this in atomic structure. Agree? Disagree? Yep. So how is radiation related to chemistry? This is how it is related, Saja. Look at this atomic structure. Electrons get knocked out. Why they got knocked out? Two atoms, they collide. Because of energy. Why? Because of temperature. So the electrons get knocked out. Vacancy is there. Again some electron comes back. So you will see a photon is emitted. That photon is nothing but electromagnetic radiation. So any photon is nothing but light, electromagnetic radiation. So whenever there is some object with certain thermal energy, there will be collisions, there will be accelerations, there will be velocities, and you will see energy is radiated. Energy is going to come out in the form of photons. Now remember, photons, light, electromagnetic wave, all these are very, very similar terms. Light is an electromagnetic wave. Photon is the particle nature of electromagnetic wave, right? Light has dual behavior. I hope you know that. Light can behave like a wave, it can behave like a particle. So that's the particle nature of light. So now whatever properties you have studied about light or electromagnetic waves, maybe in your 9th, 10th grade, or some of you might be 12th standard students, all those properties are applicable. It's nothing but light. Even me, right now, I am emitting light. The molecules of my hand, my face, neck, everything, they are vibrating, they are radiating energy. Then you'll be like, sir, is that why you glow? Nah, that's not why I'm glowing, that's because of the studio lights. I am also radiating energy, but you will see in some time the wavelengths which I am emitting, out of my body are not in the visible spectrum. In fact, how many of you know what is the wavelength that your body generally emits? What do you think is your body going to emit? What kind of wavelengths is it going to emit? Is it going to emit X-rays? Is it going to emit gamma rays? Is it going to emit ultraviolet rays, infrared, radio, micro? What kind of waves do you think it emits? Yes. Think. Yep, Abhinav. Correcto. Infrared. Infrared is beyond red. You cannot see it. That's the reason you cannot see me in the dark. I will repeat. Why can't you see me in the dark? Because you cannot see infrared. And I am emitting infrared. That's why you need these lights to see me. Make sense? So, I hope this is clear. Now, that's why you have these infrared night vision goggles. What is this infrared night vision goggles or cameras? These cameras are specially equipped to capture not just visible but also infrared light. So, all the humans present around, all the warm-bodied animals, anything, living beings around you, the warm bodies are going to emit infrared rays, and those infrared rays can be captured by those special equipment, and that's how you can see them even in the dark. Snakes are known to capture infrared, and that's why a snake can see you even when it is dark outside, because it senses your heat. So, how do you escape from this? You wear a cold jacket. You wear a jacket which does not let your radiation out. That's the way you can be invisible to a reptile like snake, which now will not be able to see you because you are blocking the infrared radiation. Understood? Isn't it interesting? Ankit sir is emitting positive vibes. Yes. And is radiation dangerous? Certain kinds are, certain kinds aren't. Like infrared, no, it's not. Ultraviolet, yes. X-rays, dangerous. Visible light, no. Normal radio waves, no. So certain waves are dangerous, certain waves are not dangerous. That's how it is. What about face? Kamal Raj, you need to cover your face also with the transparent cold kind of material. It should be cold, it should be transparent, obviously you should see it, or else if you cover it completely then you will not be able to walk or not be able to understand what's happening around you. Perfecto. So, what is radiation? It's nothing but light, it's nothing but electromagnetic waves, certain properties of it. All the properties of light are valid here. Light travels at this, obviously, 3 into 10 to the power 8 meters per second. So, it is basically very quick, and I'll just put it up over here. Okay. So, it is very quick mode of transfer. The first point just refers to it being very quick. So, it is really quick. The second point, they do not require any medium. They don't require any medium. Very important, because light can travel even in vacuum. And remember, the moment any radiation enters a medium, depending on the refractive index, the speed will change. Okay, that's obvious because it will follow all properties of light. Is this clear, my warriors? Perfecto. All bodies above absolute zero will emit radiation. Why is this true? Think, if an object is at 0 Kelvin, then there is no thermal energy. No thermal energy. So if there is no thermal energy, then there is no radiation which comes out of it. Then there is no radiation which will come out of it. But if there is any body whose temperature is more than 0 Kelvin, then definitely it is going to emit radiation. These are nothing but electromagnetic waves. These are nothing but electromagnetic waves. That is radiation. Is that clear? What is the wavelength of IR waves? It will be slightly longer than the red's wavelength. Red's wavelength is, close to 7000 Angstrom or 700 nanometers. So it is slightly more than 700 nanometers. Is that okay, Tamil? Alright. Is radiation related to electromagnetic waves? Radiation is electromagnetic waves, Suchi. Radiation is electromagnetic waves. So this phenomena is called as radiation. So these EM waves, this entire process is called as radiation. Radiation means light. Bluetooth, Wi-Fi, microwave, infrared, ultraviolet, X-rays, gamma rays, all these come under the same bracket, come under the same category, electromagnetic waves. Radiation means the light or the waves which come because of temperature. You might be wondering, sir, why don't I just call it light? Why don't I just call it EM waves? These electromagnetic waves are coming because of temperature, because of thermal energy. That light which comes because of thermal energy is called as radiation. I hope this is clear. Yep. So X-rays are dangerous for when you are exposed for a long time. For a short time it is fine. But they basically do not pass through your bones. So obviously it is used in X-rays scans to detect a fracture, because they can pass through flesh but they cannot pass through bones. Alright, moving ahead, radiation is not all that bad. It is also good, obviously. Without radiation, life won't sustain on Earth. Without the energy from the sun, there won't be plants, there won't be daylight, you cannot eat anything, nothing will grow, there will be no life on Earth. So yes, radiation has harmful effects, only certain wavelengths, but yes, certain wavelengths have very good effects, and one such effect is obviously the photosynthesis that occurs in plants, because of which life sustains on Earth. Now, I hope everybody is clear, and if everybody is clear, give a thumbs up. Perfecto. Okay, yes, perfecto. All right, great. Yes, EGL, I am. All right. Now, the light, the waves, the radiation which falls on something. Let's say I'm standing in front of the sun. When I'm standing in front of the sun, okay, outside, there are three things that can happen. Out of that incident rays, a part of it I can absorb. That's why my body gets hot. A part of it will get reflected. Obviously, some light will get reflected, and maybe some of the light might even pass through me. Okay, some of the light can even pass through me, but usually hardly any light will pass because I can see my shadow on the ground. But if I hold a glass, then most of the light will pass through it. If I hold a mirror, most of the light will be reflected. If I wear a black t-shirt, most of the light will be absorbed. So the proportions can be different depending on the type of the material that you have placed in front of the radiation. But these are the only three things that can happen: absorption, transmission, and reflection. Based on how much is absorbed, how much is reflected, and how much is transmitted, you decide the three parameters of a body. So let's say I called the incident amount of energy which is falling per unit time as Qi dot. What is this Qi dot? See this. Qi dot stands for derivative of the heat which is falling per unit time. This I stands for incident. So this is rate at which energy is incident. Energy is incident per unit time. So obviously the unit will be joules per second. Some people also prefer writing this as incident power. Okay, incident power. This is also fine. Incident power. All of these things mean the same. Rate at which energy falls, rate of energy flow is nothing but power. So incident power. Now, obviously there will be some amount of energy which is reflected. So I'm just going to call it as Q dot R. The dot stands for derivative. If I don't put that dot, then there is no derivative. So that dot symbolizes first derivative with respect to time. Similarly, absorbed will be Q dot A and transmitted will be nothing but Q dot T. Based on these variables, I define three constants, three parameters for the material. The first one is called as absorption coefficient. How much is absorbed out of the incident radiation? So the absorption coefficient is how much is absorbed upon how much is incident. How much is absorbed upon how much is incident. Is that clear, my warriors? Perfecto. Next, you have the transmission coefficient. Maybe 100 joules is incident, but only maybe 40 joules transmits. So 40 out of 100, 4 by 10, 0.4, that is how much is the transmission coefficient. So it is nothing but how much energy gets transmitted upon how much energy is incident. Last thing, reflection coefficient. It is nothing but how much energy gets reflected upon how much energy is incident. That's it. So these are the three different coefficients: absorption coefficient, reflection coefficient, and transmission coefficient. Perfecto. So I have put it up in front of you over here in the printed form as well, the coefficient of absorption, coefficient of reflection, and coefficient of transmission. Perfecto. Now I have a question for you. Guys, think, is there some relationship between these three? Can you quickly guess what could be the relationship between A, T and R? I feel they are related to each other. If I talk about the relationship A, T and R, I think they will be related. Think, whatever is incident will be reflected, absorbed and transmitted. So if you use the law of energy conservation, you will see the amount of energy which is incident will be distributed in something which is absorbed, something which is transmitted, and something which is reflected. Now if you divide the entire thing with Q dot I, divide it with Q dot of I, incident energy per unit time, incident energy per unit time, what am I going to get? Just think, what am I going to get? This is just one. This absorption and absorbed energy by incident energy, what is that? That is absorption coefficient. This is nothing but transmitted energy upon incident energy, that is transmission coefficient, and this reflected energy upon incident energy, that is reflection coefficient. So this is what you are going to get. So A plus T plus R will be nothing but 1. Very good. Amazing. Excelente. Perfecto, Saja. Yep. Now I have a question for you. For a very good glass, so let's take some examples. So for a good glass window, for a good glass window, what do you think? Which variable can you comment about? A, T or R? Which variable is easy to comment? Think about it. Out of A, T and R, which one do you think you know? Think. Yep. Yes, Waves Hari is not yet completed in Nurture series. Last year I had completed in Flash series. So if you are eager to watch it, you can watch the Flash, but wait for some time. I will complete it in Nurture series in the coming few weeks. Yep. Okay. Yes, the transmission coefficient will be 1. Okay. And another example, for a good mirror, reflection coefficient will be 1. That's how it works. Okay, for a very good mirror, reflection coefficient will be 1. Perfecto. Let's start solving some questions based on this concept. Okay, so is it possible to get perfectly 1? That's another question in front of you. Can I get T exactly equal to 1? That is ideal. That's like an ideal student. An ideal student should do all the homework. He solves all the questions. He does not have any pending tasks. He sleeps at 11 o'clock. He gets up at 6 o'clock. And it's basically your neighbor's kid. Hai na? Your neighbor's kid. And that neighbor's mom will be telling about you. Look at him. So your mom is or dad is comparing you with your neighbor is comparing that kid with you. So actually speaking, there is no such ideal kid. Agree, right? Yeah, there is no such ideal kid who does everything. So there is always comparison happening. And if you just call up your neighbor and you just ask what happened, hey, my mom told that you are doing this, you are doing that, you are so good, you are so doing that, then that kid will be like, hey, you know what? My parents are also scolding me that he is doing so well, he is doing this, he is doing that, he is so punctual. Yeah, anyways, leave it. Let's go ahead. The coefficient of absorption of a surface is 0.6 when the radiation energy is incident on the surface at 1500 joules per minute. The energy reflected in 5 minutes is 450 joules. Find the coefficient of reflection and transmission of the surface. Let's see. Yep. Let's see. It's very important, ray optics in JEE. It's a very important topic because you can get good quality questions in ray optics. There are a lot of variations that can happen. So it is very, very significant for JEE Mains as well as Advanced Tamil. All right. Any micro courses on platform class 11th aspirant? Jayant, there are a lot of micro courses for class 11th. My micro courses are also there. My HC Verma course, derivation course, numerical problem solving course, Irodo course. Only mine 4 courses are available. So there are so many more courses of other teachers also available. So if you are in the vPro, it's available for free of cost for you. Okay. So let's see how many of you got this. Come on, my warriors. Let's think about it. So first of all, start seeing what you know and what you don't know. I feel the coefficient of absorption is given. So that means A is basically 0.6. The radiation energy is incident at 1500 joules per minute. So energy per unit time is given. So QI rate is given 1500 joules per minute. The reflected energy in 5 minutes is 450 joules. So the QR is basically nothing but 450 joules in 5 minutes, which is nothing but 45 by 5 is 9. So 90 joules per minute. Now I think we can start solving. I have to find the reflection coefficient and transmission coefficient. So reflection coefficient by definition is this value by this value. Q dot R divided by Q dot I. So it will be 90 divided by 1500. 10 goes, this divides by 3, this divides by 3, this will become 50. So 3 by 50, correct? So that's going to be 0.06. So that's your reflection coefficient. That's your first answer. Now R I know, A I know, T I don't know. Obviously, you're just going to use A plus R plus T is equal to 1. A is given to be 0.6, R is given, or we just figured it out to be 0.06, T I do not know, the addition is 1. So T is basically 1 minus 0.6 plus 0.06 is 0.66, wherefore T is equal to 0.34. That's the answer. Is it there somewhere, 0.06 and 0.34? Yes, it is there. Perfecto. Okay, very good, very good. Interesting. Ankit is saying, sir, I'm looking blue. Ooh. आज blue है पानी 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 और तू भी सानी 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 तू भी सानी सानी. Okay. Option B is correct. Perfect. Yep. Do we have a strategy or guidance session on platform? Jayant will plan something if you need so, but on YouTube for sure I'll plan some guidance session. Just give me some time, let me complete few more topics and definitely I'll conduct a guidance session as well. Perfecto, perfecto. All right. Irritating woman has arrived at our house, Suchi says, but Suchi has just retracted that message and now she has gone. Very good. I'm happy for you, Suchi. Now let's go to black body. So, what is a black body? You will be like, sir, black body, you don't know what is a black body? A body which is black. I was like face palm. I was like, no, a body which is black need not be a black body. Students' reaction is like, what is sir talking about? Really? A black body can be orange, a black body can be yellow also. Students are like, what? What the hell just happened? Sir is saying black body can be yellow. Yes, black body can be yellow. Black body can be orange. It's just a body which can absorb everything. Okay, I have a question for you. This screen is black. Okay, this remote is black. My shirt is black. This pen is black. What is the meaning of black? Is black a color? Is black a color? No. Yellow is a color, orange is a color, green is a color, red is a color, infrared is also a color, but you cannot see it, that's another story. Ultraviolet is also a color, something which you cannot see again. Black is the absence of color. Your eyes, your brain perceives lack of color as black. Black is not a wavelength. there is no wavelength for black. Something which absorbs everything is black. Then, ideally speaking, you should not be able to see black. Black is just dark, nothing. The reason why you can see black, you can see the button shapes, you can see the roundness, you can see the squares, rectangles of this remote or the buttons or the pen, because it is not perfectly black. If this was perfectly black, then you will never be able to make out the edge, the corners, the roundness of the shape. Because how do you perceive edges? How do you know whether there is an edge, there is a round here, there is a curvature here? Only because the reflection of light is different at different places. That's how you look at the edge, right? This face reflects differently, that face reflects differently, and your brain perceives, okay, these are two surfaces meeting at a point, that's an edge. That's how your brain perceives. But if it's perfectly black, everything is absorbed, nothing is reflected, gone, you will not be able to see it. Yep, I hope this is clear. But you do not think of a black body like an evil which absorbs everything. It gives also. We'll come to that point. A black body absorbs all radiations. The absorption coefficient is 1. A is 1. Absorption coefficient is 1. Okay? But when you heat a black body, that means any temperature more than 0 Kelvin, it will emit radiation. It will emit radiation. Even this remote is emitting radiation. Emitting, that means it's coming within, from it, emit radiation. Emission is a phenomena which happens from the body. Reflection happens because of some other source's light falling on it and it bouncing back. Emission is happening from the body because of the temperature, and that can happen even at higher temperatures and lower temperatures. And you will see the moment the emission starts, you will start seeing different colors of that black body. Usually the color of the black body is in infrared, that's why you do not see it. But if you heat it hot enough, then you will start seeing different colors. It can become red, it can become orange, and that's why I said a black body need not look black. That's how it is. Okay, now how do you create a black body? It's very easy. You take a sphere, you have a small opening over here. So what I have done over here, I'll just tell you, very interesting thing. You basically take a sphere, you keep an opening and let the light fall from that hole on this surface and let it get reflected multiple times. What happens is the light which falls inside, if the coating inside is black, let's say 98% of it gets absorbed. In the next reflection, the remaining lights 98% will get absorbed. In the next reflection, the remaining lights 98% will get absorbed, 2% will move. So within few reflections, the light will just die out. This body will act like an ideal black body, because whatever enters through that hole, everything will get absorbed because of multiple reflections. So that's how you can create a very good black body. Is that understood? My lectures are also black body. Yes, we have shifted to dark mode. Now, if this much is clear, we'll go ahead. Yep, if this much is clear, we'll go ahead. Now, like I said, a black body can also emit from itself, and depending on the temperature, you will see different colors coming out of it. But when you heat it to very high temperature, you will see almost all the wavelengths coming out of it, and it will look something like this. Our sun is a black body. You'll be like, what? Sun is a black body? I thought it was a yellow color body. It's yellow because, not of reflection, because of the temperature of the sun. If the temperature of the sun was something else, then it would emit some other color which would be outside our visible range, and then the sun would look like a dark body. It's just because of the fact that the radiation coming out of the sun is in yellow region, that's why I see it yellowish in color. That's it. Yep, I hope this is clear. So, otherwise the sun is actually a black body. Okay, do one thing. Take some water. You carry a bucket of water, throw it on the sun. A huge bucket. Okay, so imagine you have a huge bucket, throw it on the sun. Extinguishes. Okay, steam coming out of it, gone. You know, the sun will look black, perfect black pitch, gone, gone. No life, nothing. Okay, so that's what will happen if you extinguish the fire on the sun, and otherwise you see all the colors coming out of it. All right, perfecto, perfecto. Now, based on this, it's not possible, Kalyan, it was hypothetical, it's just imaginary, just imagine it to be. Yeah, Aniket understood that, just imagine it. Now, any normal body and any black body, if you compare like how much it is emitting, how much radiation is coming out of it, you will see black body, although it absorbs a lot, it is also a very good emitter. Black body emits much better than a normal surface. If you have a steel surface, like this steel surface, this is not a black body. If you have a plastic surface, it's not a black body. A steel plastic surface will emit less at the same temperature as compared to that of the black body. And that comparison happens via a factor called as emissivity. Emissivity. What is emissivity? Emissivity E is nothing but the ratio of how much a normal body emits upon how much does a black body emit. So this number, this is a dimensionless number, is nothing but how much does a normal body emit per unit time upon the energy of a black body, Can you now guess, usually for normal bodies, usually what do you think will be the value of E? For steel, plastic, cement, brick, road, humans, anything, cloth, what do you think will be the value of E? Usually, everything emits lesser than the black body at the same temperature. So the value of E will be less than 1 because numerator will be less than the denominator. Okay, normally E is less than 1. I hope this is clear. Perfecto. Carbon black is very close to ideal black. Yes, very close. The A will be, the absorption coefficient will be very close to 0.98, 0.99, 0.97 like that. Okay. Lamp black is a material which is very dark and its absorption coefficient is close to 0.97, 0.98. Okay. So if you want to make it perfectly black, then you have multiple reflections, it will absorb everything that is there. Perfecto. Moving ahead to the next thing. Wien's displacement law. We will talk about the colors, and for that I will show you a simulation. Just 1 second. Let me bring this simulation. Wien studied how does the light wavelengths, differ at different temperature, and he studied the different wavelengths coming out of a body which is hot at this temperature, this temperature, this temperature, and he found that at any given temperature, he found that you don't get equal wavelengths of all the values. You don't get red, yellow, green, violet, infrared, X-rays, in equal amounts. But you will find that there is one wavelength which is very dominating, and other wavelengths are there but less in number. This graph reminds me of a particular thing. This reminds me of the kinetic theory of gases. Remember the Maxwell's speed distribution, most probable, average. Remember that? It's very similar to that. Yep. So, sir, the black body will emit much radiation when it gets very hot. Yes, Jin the editor, definitely. Oh, no problem, Ankit. Is there any instrument to measure the radiation because we cannot see them? Oh, there are many experiments. Young's double slit experiment, diffraction experiments, spectrometer. These are all different experiment setups to detect the wavelengths of light. Definitely. You also have prism, and you can make the light pass through the prism and it can affect a photographic plate. So many instruments like that are there. So there's a particular wavelength which dominates other wavelengths. You can see this x-axis is wavelength, y-axis is how much energy is there in that wavelength. More the energy, more the dominant the wavelength is. So other wavelengths are less dominant. Now he increased the temperature, he changed the temperature of different bodies and he studied it, and he found that the wavelength, which is maximum, and the temperature are inversely related to each other. He found it is inversely related, and this is what you're going to see. Look at this. This is a thermometer. If I increase the temperature, you will see this graph shift. And think about it, why it is shifting the left side. Look at this, it is shifting towards the left side. I know the scale is going out of the bound. So the maximum wavelength is shifting. Look at that. So if I increase the temperature, 8500 Kelvin, I'll just zoom out. You can see it has shifted onto this side. It's more the temperature, less the wavelength. Less the temperature, more is the wavelength. The wavelength is coming this side. So I will zoom onto it so that you can see it. Okay, if I decrease the temperature, you can see the graph is shifting towards your right hand side. Can you see that? The maximum wavelength is shifting towards the right hand side. Can you see that? It shifts. So reducing the temperature shifts it towards the right, increasing the temperature shifts it towards the left. That's why it is called as the Wien's displacement graph. Inversely proportional. Yep, KTG in physics is similar to the KTG in gaseous state. Yep, whatever you study in chemistry. Perfecto. Inversely proportional. Yes, Kalyani. Hello, Feroz. So going back to our slides over here. 1 second. Yep, there we go. So this is called as the Wien's displacement law, and he found that the maximum wavelength which is emitted is inversely proportional to the temperature, and this comes out to be like this. T into lambda max is the Wien's displacement constant. It is 2.98 into 10 to the power minus 3 SI units, but you can also think of it like this, 3 into 10 to the power minus 3 SI units, 3 and 3, so that you do not forget. So 2.98 is very close to 3. That's how you can remember that. So this is a very, very important relationship that you must definitely remember. Inversely related to each other. All the wavelengths are emitted from here. You can see that. This is basically your lambda max. Okay, this is your lambda max. This is what I'm going to call it. Other wavelengths, other lambdas are less in proportion. That's what I would say. That's why everybody will emit different colors when you change the temperature. Have you noticed when you heat iron, it becomes red, then it becomes yellow. Now I hope you understand why it happens like that. Look at this graph, you will understand it. When you heat the iron, what happens? Normally the lambda max is here. Do you see it? It's outside the visible spectrum. When you heat that iron and suddenly it reaches some temperature, you will see it will come in the red region. It will come in the reddish region. The wavelengths will come in the red region. That's why it becomes reddish hot. After some time, after red, it becomes yellowish. After red, it becomes yellowish. Now I hope you guys got it. While lambda is used for wavelength, it's just a symbol. Okay? So don't worry about it, Suchi. It's just the way it is historically. Alright. So moving on to some questions maybe. Yep, there is a question coming up on your screen. The solar radiation emitted by the sun resembles that emitted by a black body. Our sun is a black body. It resembles the black body radiation at a temperature of 6000 Kelvin. So that's the temperature of the sun, and that's how it is emitting the radiation. Think of a black body at 6000 Kelvin emitting thermal radiation. The maximum intensity is emitted at a wavelength of 4800 Armstrong. So the peak of that graph is at 4800 Armstrong. If you cool the sun to 3000 Kelvin, then what will be the maximum intensity? Where will the maximum intensity be? At which wavelength will it be? Yep. Will mirror absorb radiation? Ideal mirror, no, but a real mirror will, yes, it will, because no mirror can be made in reality which will not absorb at all. So there will be always some amount which will be absorbed. So all you need to use is Wien's displacement formula. Wien's displacement formula. So lambda 1 T1 will be lambda 2 T2. Lambda 1 is nothing but 4800. T1 is 6000. Lambda 2 I do not know. T2 is nothing but 3000. 6000. So therefore lambda 2 will be 4800. This 3000 and 6000 will cancel and it will become 2. So this will become 9600 Armstrong. Is it there somewhere? Yes, it is. Option B. Done, done, done. I hope this is clear, my warriors. Perfecto. Yes, Saja, it is option B. So what have we done? We have just thought about the maximum intensity is at certain wavelength at certain temperature. When you change the temperature, the maximum intensity will be at a different wavelength. So this peak will shift. That's what happens. It's perfect. Option B. Moving on to the next question. Very interesting one. There is an ideal black body at a room temperature. It is thrown into a furnace. It is observed that it is the darkest body at all times. It cannot be distinguished at all times. Initially it is the darkest body. Later on it becomes the brightest. Initially it is the darkest and later it cannot be distinguished. Very interesting. Come on, my warriors, figure this out. Think, think, think. Okay, no problem, Jayant. I hope you will watch the lecture in a replay mode after your dinner is over. Alright, Abhinav saying C. Interesting. Come on, think about it. Yes, Jin the editor, you can ask your doubt about the black body. It's okay. Come on, come on, come on. Can I watch your videos? Yes, Michael. Definitely, even a NEET aspirant can watch it. But yes, please remember there will be questions which are of JEE Mains plus Advanced. So that's okay. In fact, you will be better prepared for NEET. In fact, there are good chances that by attending JEE classes, you will get 150 to 180 marks in physics alone. So yeah, if you want 150 to 180 marks, so definitely go ahead with it, Michael. So well, see, the correct answer is actually C. Yep, most of you are correct. I'm very happy with that. The reason is, look at this graph. I just had shown you. I'll just show the simulation back again. Normally a black body, when it is cool, it will hardly have any radiation in the visible zone. The lambda max will be here. But when you heat it, when you start heating it, the lambda max will come in this zone. It will start emitting all the colors. As you heat it, it will go even this side. So many colors will be emitted. And remember, black body emits the most. So it will be brighter than the other objects at the same temperature. Remember, just some time back, just some time back, I had given you the formula for emissivity. Here we go. Yeah, emissivity. Emissivity for a black body is always more than that of a normal body. So black body will always emit the most, and that's why it will look the brightest as compared to the other objects. Perfecto. Now that brings us to, a very interesting law called as the Kirchhoff's law. So yes, Amrit Varshini, I do remember you, bacha. Long time no see. See, for a black body, what is the value of A? I just told you, it's a very good absorber, right? It absorbs everything. So A is 1. And black body is also very good emitter. It emits the most as compared to any other body around it at the same temperature. The emissivity is 1, right? That's for a black body. For any other body which has some A and some E, you can easily prove that the value of the absorption coefficient and the emission coefficient for any other body is always equal. It's always equal. Yep. Will the black body emit the most powerful radiation than any other body, not any other color, when you give heat? Yes, not any other color. Black body will emit many colors and in greater amounts as compared to other body, at the same temperature. I hope, Jin, that is clear. So, the black body, A is 1, E is 1. That's where you can see A is equal to E. But for even other bodies, any normal body also, which has some absorption coefficient, some emission coefficient, you will always find that the value of A and E are equal. This is very, very important. For a black body, I just told you, the A value was 1 and E value was 1. So both of them were anyways equal. Both of them were anyways equal. And this is also true for even other bodies. So good absorber is also a good emitter. A good absorber. What this law, Kirchhoff's law, says is that a good absorber is also a good emitter. Is also a good emitter. Makes sense, kind of, even in real life. A student or a kid who can absorb everything what the teacher is saying is also probably the student who is going to give back to the society, who is going to emit and spread his knowledge, for the better of the society. Yep, that's how it is. Yep, so very interesting. Now, if you have been to Rajasthan, the Sahara Desert, or Dubai, or maybe any kind of desert, you would have seen that during the day it's very hot, but during the night it is very cold. And you might have often wondered, why does this happen? Let's see the reason behind this. The days are very hot, the nights are very cold, because the good reflection is also good emission. The good emission is also good absorption. The good absorption is also good reflection. The good emission which is happening is also good absorbing and good reflection which is happening. Very interesting. Very good, Suchi. Right, Kalani, let's see. Come on, my warriors. Vishal, looks like you loved that explanation. So, why is this happening? Think. Okay, during the day, what do we have? During the day, what do we have? This is daytime. Okay, this is the camel. So this is the camel which I learned to draw in 3rd standard. Is this how a camel looks like? Yep, this is a camel. Oh, I have to draw the hump. Okay, so you have the sun. Sun is yellow in color. So let me just show the sun. Okay, perfect. This is how our beautiful sun looks like. The radiation from the sun is incident. This is your incident radiation. Incident radiation. Now it so happens that the sand which is there over here, the sand, the absorption coefficient is high. It is very, very high. Close to 0.9, 0.8. So it's in the large region. If it's a good absorber, what will happen? It will become hot easily. It will become hot easily. That's what happens during the day. Now what happens once the sun sets? So in the night, this sand is hot. The outside temperature is cold. Okay, the skies are gone blank. There is no heat. There is no sun. This will now start emitting, and since A is large, even E is large, it will emit very quickly, and it will emit really fast. So all the heat is lost, gone. So the ground will become colder. So that means the ground becomes cool faster. It becomes cool really fast. That's how it is. I hope this is clear. Oh my god, Suchi Mama saying desert plants open their stomata at that time. Oh my god, I remember that word. Okay, let's not get into bio now. I'm not that great at bio. Stomata, I like that name, stomata. Okay, I think if you know some terms deeply about black body, we can scare small kids and then we'll be hero and highly knowledgeable person to the kids. Easiel, very evil. Look at Easiel, very nice Easiel. You can scare kids, forget black body, you can even scare kids with these symbols. Just do this and just do this. Just you want to scare kids, just do this. X square dx. And then just do this. It becomes like this. The kid is like, what just happened? How did this become x cube and how did this become 3? And what the hell is this C doing over here? They will lose their sleep in the night. They'll keep on wondering, what just happened? Should I even write my 10th standard exam and go to 11th grade? Should I even study this? Yeah, so that's how you can scare kids. Alright. Okay, now that we have spoken so much about the colors of radiation, we have spoken about the, which body emits more, which body absorbs more, and how the absorptions and the emission coefficients are equal using Kirchhoff's law. Now it's the time to check how much energy is going to come out of any body. We have spoken about colors, we have spoken about black bodies and normal bodies. It's time to focus on the energy, net energy which comes out of it. You see a hot iron rod like this, you can already feel the heat. I am feeling the heat. More the temperature, more the heat. Correct? More the temperature, more the heat. More is the emission coefficient. That means the emissivity is more. Then it will emit even more heat because it is closer to a black body. Black body is a good emitter. Also, if the area is more, if it's not a thin iron rod, but if it is a big iron rod, more amount of heat will be coming out of it, more amount of energy, because throughout that surface area, more energy will be popping out of that surface. That means the energy which is coming out of that surface is dependent on three things. Three things, my warriors. Number one is nothing but area of the surface. Number two, temperature of the surface. Number three, the material of the surface. And that's what you can see in this graph right over here. This is the amount of power radiated. Power is energy per unit time. Radiated, that means which is being emitted out of it. You see the x-axis, that's temperature. More the temperature, more the power. More the temperature, more is the power. Not just that, if emissivity is more for the same temperature, you have more power. Yep, and area can be also plotted, but yes, let me put that thing for you. The amount of energy radiated, okay, I'll just put it over here. The energy radiated or emitted per unit time, okay, depends on three things. Number one, temperature of the surface, area of the surface, and also the emissivity of that material. And when you plot these graphs and you find out to which power is it proportional to, that's what Stephen Boltzmann did. They formulated a law based on experiments, based on this graphical analysis, based on what power is it proportional to. So it turns out that this energy which is radiated per unit time, I can call this as Q dot E. E stands for emission. What is this E? This is how much it is emitting. You can also call it as PE. Oh, I don't need that dot anymore then if it's power. Just one second. Dot is not needed. So this energy which is radiated, emitted per unit time turns out to be Q dot E is equal to E sigma A T raised to 4. This sigma is nothing but your Stephen Boltzmann constant. That is the constant of proportionality. Interesting thing to note, it is proportional to T raised to 4th power. You can see it's not a straight graph, it's a curved graph. It's proportional to T raised to 4. Bhavisha Daroleju, I hope you see the bottom session title. This is the nurture series. This is the nurture series, okay? It's modified because, I want to conduct power-packed sessions for all of you. So it's the same nurture series. The thumbnail looks different. Don't get confused, bacha log. Okay, this is the nurture series. You can see it. It's there in the title. All right. This is nothing but going to be 5.67 into 10 to the power minus 8. Very easy to remember. 5, 6, 7, 8. 1, 2, 3, 4. Get on the dance floor. 5, 6, 7, 8. Stephen Boltzmann constant. Understood, my warriors? 1, 2, 3, 4. Get on the dance floor. 5, 6, 7, 8. Stephen Boltzmann constant. All right. Great. Okay. So this is what you should remember. E is the emissivity, A is the area, T is the temperature. Perfecto. Got it? Let's move on to a question coming up on your screen. A spherical black body with a radius of 12 centimeter radius 440 watts of power at 500 Kelvin. 500 Kelvin. If the radius was halved, temperature was doubled, the power radiated in watts would be how much? Let's try and do this question. Let's draw it first. This is a spherical black body. It has certain radius r, and obviously it's going to radiate some amount of energy. Okay, it's going to radiate some amount of energy everywhere. This amount of energy which is radiated is given by E is the emissivity, sigma is the Stefan-Boltzmann constant, A is the area of the sphere into T raised to 4. But since the radius is changed, what will happen? The area of the sphere will change. So instead of putting area, I'll put 4 pi r square, which is the surface area of the sphere. So E sigma into 4 pi r square T raised to 4. Interesting. Now, if you notice, E sigma 4 pi are constants, only r is different. That's it. So just divide the 2. So Q dot E in the first case upon Q dot E in the second case will be E sigma 4 pi gone. So it will be nothing but R1 by R2 square and T1 by T2 whole raised to 4. QE in the first case is 440. Second case I do not know. Q dot E in the second case I do not know. R1 by R2, the radius is halved. Look at this, the radius is halved. So R2 is half. So initial radius was double, so 2 square. I hope this is clear. The radius is half. The new radius is half of the previous one. The older one was twice as the initial one. The temperature is doubled. T2 is twice T1. So this is 1 by 2 whole raised to 4. So this is nothing but 4 and this is nothing but 16. So this is nothing but 1 by 4. So this Q dot E of the second object will be 440 multiplied by 4. How much is it going to be? Check this out. 4 4s are 16, 4 4s are 16, 16, 160 plus 16, 176. So 1760. That should be the answer. Oops, EGL Sangram, it's not 110, be careful, it's 1760. That is option D. Done, done, done. Understood, my warriors? Perfecto. Yep, very good. Meta! I'm not a ma'am, I'm a sir. Oh my god, I should really keep my beard. Wow, crazy. There is session title, Shreyas sir written over here. I sometimes doubt whether you guys are like really joking or what. Anyways, moving on. Now, this is by far the most ignored theory even in coaching. Many people don't even talk about it. But there are questions in JEE based on this. See, if you take two objects, let's say you and your best friend, you're very hot. Your best friend is very cold. Don't take it otherwise, okay? Maybe you're very cold and your best friend is very hot. Don't take it otherwise, alright? And you are sticking to each other. You're sticking to each other. So what will happen? You're sticking, that means conduction. Hot body will transfer heat to the cold body, right? Hot body will transfer. Trinku, we are coming to questions. Hot body will transfer heat to the cold body. Interesting. Once both of you are at the same temperature, there will be no exchange of heat. There will be no exchange of heat, right? Perfect. Now, in radiation, things are very different. You are hot body, your friend is a cold body. You are hot body, so you will emit. Cold body will absorb. That's what you think, but that's not the case. In fact, what happens is, even when the temperatures are equal, let's say you and your friend are both at the same temperatures, even then the heat will be exchanged between the bodies. Just that the amount of heat which is emitted will be the amount of heat which is absorbed. So there is no net heat transfer even in thermal equilibrium. So radiation is a very good exception where the heat transfer occurs even at thermal equilibrium, but the net heat transfer is zero. I will repeat, in conduction when bodies touch, then heat transfer stops when thermal equilibrium is reached. But in radiation, even in thermal equilibrium, heat transfer occurs both ways, but it is equal. Hence the net heat transfer is zero. I hope this is clear. I hope this is understood. All right, perfecto. So this is what the three important points of Prevost's theory of heat exchange are. The rate of emission by a body does not depend on the temperature of the surrounding. So you will keep on emitting irrespective of whether the surrounding is cold or hot. You will always emit. So even when thermal equilibrium is reached, you will always emit it. Number two, a body at higher temperature than the surrounding radiates more heat as compared to how much it absorbs. So if you have a hot body, it will emit more, absorb less. But if you have a body which is at the same temperature, it will be equal. And if the body's temperature is lower, then it will absorb more and radiate less. It will absorb more and it will radiate less if the temperature is less. Based on these three, you can combine it into one single law. So observe this. If you have a body, its temperature is T, it is emitting some energy Q dot E. That Q dot E, I just told you, is E sigma A T raised to 4. But there might be some surrounding. This is probably the surrounding. So this is surrounding, and the surroundings temperature maybe is Ts. That radiation from the surrounding might be entering inside the body. So the amount of energy which is absorbed will be E sigma A Ts raised to 4. Actually it is not E, but it is nothing but A. So it is A sigma A Ts raised to 4. How much energy gets absorbed? But remember Kirchhoff's law? Remember Kirchhoff's law, A and E are equal. So therefore Q dot A is nothing but E sigma A Ts raised to 4. This is using your Kirchhoff's law. Using your Kirchhoff's law. Okay, because A was equal to E. Now this is the amount of energy which is coming out. Q dot A is the amount of energy which is absorbed. So the net heat transfer, Q net, which will be how much energy is being absorbed entering minus how much energy you are emitting, which is going out. This number Q net will come out to be, check this out, if you subtract this with this, how much will you get? E sigma A Ts raised to 4 minus T raised to 4. This is the formula that you are going to get. Understood, my warriors? Got it? Is equilibrium also hypothetical? No, it's not a hypothetical, it's a real concept. So two bodies can be in thermal equilibrium. Okay, it's not hypothetical. Is that understood? Clear? Okay, so this is the net heat. And do you see over here, if Ts is equal to T, what will happen? This bracket term will become 0. No net heat transfer. Net heat transfer will stop. If surrounding temperature is more, then the body will absorb heat. If surrounding temperature is less, body will emit more heat. I hope this is understood. Alright, let's solve a question coming up on your screen, and here it is. Two identical objects A and B are at temperatures T and I think it should be TA and TB. Okay, I think that A subscript is missing. This is TA and TB. Respectively, both objects are placed in a room with perfectly absorbing walls maintained at temperatures T. If TA is more than TB, the objects A and B attain equilibrium temperature eventually. Which of the following is the correct statement? Many students are going to make a mistake. Let's see how many of you can get this. Hello Syed, hello Keswa, Sai Priya. Welcome all my lovely warriors. And if you are new to the channel, welcome to JEE Enthuse English channel. And you're watching the Nurture series 11th standard. So if you want to watch all the classes, all the sessions which have been conducted previously, it's available in the videos. And yes, if you want to see the future classes, go hit the subscribe and hit the like button so that you do not miss my future sessions. Okay. Elks Gallery, I am posting the session notes in the Telegram, but not in the old Telegram. The old Telegram is gone. Slowly it is going to be discontinued. Join the new Telegram channel. Okay, make sure you join the new Telegram channel. In the new Telegram channel, everything is being posted. Okay, all right, great. Let's see how many of you can do this question. First of all right, let me just draw this. You have a hot body. Okay, this is A, and this body B is relatively cold, and this is kept in a chamber which is at temperature T. What will happen? Heat will come out of the hot body. Obviously, the heat will come out of the hot body, but there will be more heat which will be coming out of it. So it will be emitting more, but it will be absorbing very little. It will be absorbing less. Once it reaches equilibrium, the amount of emission and absorption will be equal. See, this is hot, this is cold. Obviously, they will finally come to the same temperature, and then at equilibrium, the emission and absorption will be same. Is there such an option? A only emits? No. A loses more than it absorbs, while B absorbs more than it radiates until the temperatures T is attained. So I think it should be option B, my warriors. Just check this out. Correct? Right? So temperature finally will be T, and that's when absorption and emission will be equal. Nothing will be more, nothing will be less. The temperature is not zero. Where is the temperature zero? It's not zero. Okay. The net temperature, there is nothing like net temperature. The net temperature will be T. Suchi Mama. All right. Okay. Moving ahead. Now, some really, you have amazing questions over here. So watch these questions carefully, because now these are of slightly higher difficulty order. This is a hot black body which loses heat at 30 joules per meter square per second, per area, per unit time. That's the energy which is lost. And the most intense radiation is at 15,000 Armstrong. When you change the temperature, increase it, then the most intense radiation comes at 7,500 Armstrong. Find the rate of loss of heat if the surrounding temperature is half the initial temperature of the block. Very good question. Multiple laws are involved. Let's start one by one. See, according to the question, it's mentioned that the lambda max, okay, the lambda max occurs at 15,000 Armstrong at certain temperature. Let's say that at T1 the maximum wavelength is 15,000 Armstrong, and at T2 the maximum wavelength occurs at 7,500 Armstrong. Fair enough. Is T1 given? No, nothing is given. The question is, find the rate of loss of heat. This is in the second case, basically in the second case when the temperature is T2. Fair enough. Now one thing is clear. Since by Wien's displacement law, lambda into temperature is nothing but a constant, lambda into temperature is a constant. From here you can see initially lambda was 15,000, then it became 7,500. It has become half. So if lambda becomes half, temperature should become twice, right? Temperature should become twice, right? So can I say from this, therefore T2 will be twice of T1? Everybody agrees to this statement? Agreed? Perfecto? Great. So that's the reason why this is happening, is because lambda into T, that's the Wien's displacement law. So if wavelength has become half, temperature would have become twice. Next thing, surrounding temperature is half of the initial temperature. Oh, from this statement, surrounding temperature, Ts will be T1 by 2. Fair enough. Now comes the best part. All right. See, initially the amount of energy which is lost is 30 joules per meter square per second, meaning using our Stephen-Boltzmann law, which is Q dot E will be E sigma A, T, the body is hot, so it will be emitting more and absorbing less. So T raised to 4 minus Ts raised to 4. If I use this, think this is the amount of energy which is radiated per unit time, the amount of net heat which is lost. Here what is mentioned is amount of energy which is lost per unit time, per unit area. So in order to find it per unit area, just take that area term over here. So Q net upon A will be E sigma T raised to 4 minus Ts raised to 4. Now this is what is given to you. This is what is given to you. The amount of energy which is lost per unit time, per unit area. This actually is nothing but intensity. This is nothing but intensity per unit time, per unit area. So I'm just going to call it as I. Is this understood till here? Everyone clear till this point? Perfecto? Okay. So now, if I divide I1 by I2, because I want to find in the second case, what is the value of I2? That's what the question is saying. If you change the temperature, then for this particular change, what is the new rate at which the energy is lost? I2 is asked. So that's why I'm dividing I1 by I2. Think E is the same, sigma is the same. Shouldn't I get T1 raised to 4 minus Ts raised to 4 upon T2 raised to 4 minus Ts raised to 4? Everybody gets this? Everybody gets this? I hope everybody has understood this. Perfecto. Now just start substituting the values right from over here. What is the value of T1? T1, okay, I'll just put it as T1, no problem, T1 raised to 4. Ts, surrounding, is T1 by 2. So this will be T1 raised to 4 divided by 2. So 2 raised to 4 is nothing but 16. So 16 comes below. Upon T2, T2 is twice T1. So 2 raised to 4 is 16. 16 into T1 raised to 4 minus Ts. What is Ts? Ts is T1 by 2. So it will be T1 raised to 4 divided by 16. And over here, what is I1? I1 is nothing but 30 and divided by I2. Fair enough? Everybody clear till this point? Let's start solving this now. 30 by I2 as it is. 30 divided by I2 is as it is. Now T1 raised to 4, T1 raised to 4, T1 raised to 4, T1 raised to 4. Everywhere it cancels out. Everywhere it is cancelling out. Okay, now just take the LCM. See what will you get? 16 minus 1 divided by 16. That's on the numerator. 16 minus 1 by 16. 16 into 16. 16 into 16 minus 1 divided by 16. 16 cancels. So I will get 30 by I2 will be equal to 16 minus 1 is 15. 16 16s are 256. 256 minus 1 is 255. 15 and 255 will go with 15 15s are 225, 225, 240, 255. That means 17 times. This will go 17 times. So therefore, I2 will be 30 into 17. 17 3s are 51. So 510. Is there 510 in the answer? Yes, it is there. Yep, perfecto. I hope this is clear. Yes, Abhinav, it is the answer. So, what and all concepts were involved? Let's have a relook. Number one, the temperature was changed, was understood because it was given the maximum intensity of the radiation which occurs, that wavelength has changed. So, if the wavelength has become halved, temperature has been doubled. So, I got the initial and the final temperatures ratio. T2 is twice of T1. Surrounding is half of T. The net heat which is emitted per unit time was given. So per unit area is just this value. And I understood just by the look of the units that this is what has been given and this is what has been asked. Look at the units, joules per second per meter square. So I just found the ratio of the intensity because I know E and sigma will cancel. These terms are already got from here and you just cancel and solve the question. Understood? Perfecto? Great. Answer is 510 joules per second per meter square. Moving to the next question coming up on your screen. Very good. Here we have a copper sphere, it is suspended in a evacuated chamber which is at 300 Kelvin. The sphere is maintained at constant temperature of 500 by heating it electrically. Very interesting. 300 watts of electrical power is needed. But now you take half of the sphere and it is blackened. That means black body, only half of it. Now, the moment you make half of it black, it is going to emit more very quickly. So you need more electrical power to maintain the same temperature. Find the emissivity. Let's try and do this question. Understand this question first. You have a sphere. Okay, you have a sphere, and obviously it is going to emit radiation, and the temperature of that sphere is mentioned. It is at 500 Kelvin. This is at 500 Kelvin. And the surrounding which is there, the surrounding is maintained at 300 Kelvin. This is the surrounding which is at 300 Kelvin. Fair enough. Now, initially, the copper surface will have some emissivity E. Copper surface will have some emissivity E. And because of this, you know, the temperature difference, it is emitting more, it is absorbing less. Think, because it is emitting more and it is absorbing less. Why is it absorbing less? Surrounding temperature is less. It will cool down. Won't it cool down? In order to maintain the temperature, you have an electrical heater. So this heater is there, which is giving it 300 watts of energy to preserve that temperature. That means whatever energy the heater is giving, that's exactly the net amount of heat which is lost by the copper sphere. I'll repeat over here. The energy provided by the heater is basically the net energy of radiation, by the sphere. Does everybody agree to this statement? Think about it. Everybody agree to this statement? Hello Vignesh, hello Bachalo. Now, can I then say that this 300 will be equal to, remember our formula, E sigma A T raised to 4 minus T S raised to 4, remember that formula? So can I say it is E sigma A is the surface area, temperature of the copper sphere, which is nothing but 500 raised to 4, minus surrounding temperature, that is 300 raised to 4. Everybody agrees to this statement? Perfecto. Hello RCM, welcome aboard. This is the first scenario. Now the second scenario says half of the sphere is copper and half of it is blackened. Interesting. So the same situation, but half of it is E, half of it is basically a black body. Half of it is a black body. It's kept in the same chamber. At 300 Kelvin. This is still 500 Kelvin. And you're still providing it heat from the heater, and you're providing it this time around 600 watts of energy. Obviously, now again, if you use the same relationship, the energy which is provided by the heater is the net amount of energy which is lost by that body. How will it look like this time? 600 will be, divide the sphere into two parts. Half of it is black, half of it is not black. Half of it will be copper, and copper will emit how much energy? E sigma, but only half of the sphere is made of copper. So the area will be A by 2. Do you understand why it is A by 2, my warriors? Because only half of it is emitting as if it is copper. This E is the emissivity of copper, and the temperature is still 500, so raised to 4, minus surrounding temperature is 300 raised to 4. I hope everybody agrees to this. Now the next thing, the remaining half will be emitting as a black body. For a black body, E is 1. This is the catch. E is 1, sigma is sigma. Area of the surface will be exactly half. So this will be A by 2. This will be A by 2. Again, the temperature is again nothing but 500 raised to 4 minus again 300 raised to 4. Now once you get these two, how are you going to solve it is the tricky part, because see what is asked. Calculate the emissivity of the copper. We want to find E. I don't want to find area or sigma. I think I can divide both of them. So just divide both of them and see. So divide. If you divide both of them, many things will get cancelled, like sigma A, sigma A, sigma and A. Do you see that? Sigma and A will get cancelled, and what will you get? 600 by 300 will be equal to, here I will have E by 2, and by the way, this 500 raised to 4, 300 raised to 4, 500 raised to 4 minus 300 raised to 4, all these things will also get cancelled. So E by 2 plus 1 by 2, the whole thing divided by, I think just E will be there over there, just E. 6 by 3 is 2, so it will just become 2E is equal to E by 2 plus 1 by 2. Take that 2 over here, so it will become 4E is equal to E plus 1. So it will become 3E is equal to 1. Naturally, E will become 1 by 3. Is it there somewhere? Yes, option A. That's how you do it. Okay, perfecto, perfecto. So Sonu Roy, what has happened? In the first situation, the body was hot, the surrounding was cold. So it will be emitting more energy. It will be absorbing, it will be emitting, but net energy will be lost. So the net energy which will be lost will be given by your Prevost theory formula, E sigma A, temperature of body raised to 4 minus surrounding raised to 4. But if it loses energy, it will become cold. How do you maintain the temperature? By providing exactly that heat which it is losing. Who is providing that heat? Heater, that coil. How much energy it is providing? 300. So whatever energy it is losing, that much exactly is being given to it so that the temperature is maintained. So 300 is equal to this. The same thing you do it next time, but keeping in mind, half of it is copper, half of it is black. So for copper, area will be half, black body, the rest half will be A by 2. For copper, emissivity will be E. For black body, emissivity will be 1. So solve that, you'll get the answer. Okay, is that understood now? Perfecto. Sonu, alright. It looks difficult, but trust me, it is a very interesting question. The last concept of today's class, and that is Newton's law of cooling. And we'll answer the first question also via Newton's law of cooling. You'll understand why it happens the way it is. Perfect. See, you might have seen this and experienced this, especially in winters. It's very evident that you have a hot bucket of water. It becomes cold very quickly. Why does it become cold very quickly? Because the bucket's temperature, the water's temperature is very hot as compared to the surrounding. But when the bucket's water cools down and the temperature comes down a little bit, but it's not yet reached the room temperature, the amount by which it cools is slower as compared to the amount by which it cools initially when it was hot. Have you experienced this? Initially it cools down very quickly, but later on it takes a long time to cool down and eventually it reaches the equilibrium temperature. That's nothing but Newton's law of cooling, as simple as that. Yes. So we will see what Newton's law of cooling is via Prevost theory. Observe the derivation, very important. Imagine you have a body whose temperature is T and the surrounding temperature is Ts. Let's say that the T value is the surrounding temperature plus delta T. This delta T is the excess. This is the excess temperature as compared to the surrounding, and let's say this is small. This is not too much. Maybe some 10, 15 degrees Celsius, 20 degrees Celsius, not much, okay, as compared to the surrounding. Because usually when we talk about temperature, we talk about it in Kelvin. So for 273, 280, 290 Kelvin, 10, 15 Kelvin is a small amount. So this delta T stands for the excess temperature. So if I tell you what is the net heat which is lost, or net heat which is gained by the body in this particular situation, the net heat which will be in this case lost will be equal to, think about it, mc dt, mass into specific heat capacity into temperature difference. All right, because there is a dot over there, that dot stands for rate of change of heat, so that's why I have to divide it with small dt over here. Those of you who did not get that, I'll repeat. Usually your Q is equal to mc, delta T. This Q is finite, delta T is the change in temperature. But when you have dq, then it will become mc dt. And when you divide dq with dt, then it will become mc dt by dt. Is that understood, my warriors? Perfecto? Great. Now, when you put in the value of Q net from your Prevost theory, which was nothing but E sigma A, and then you will have T raised to 4 minus Ts raised to 4 is equal to mc dt by dt. If you put this, okay, I just substituted the Prevost theory formula, the Stephen-Boltzmann law. Now let's solve this by putting the value of Ts plus dt, and you will see one interesting result. You will see this as E sigma A. Instead of T, you just put it as Ts plus delta T whole raised to 4 minus Ts raised to 4 is equal to mc dt by dt. Now here is what I'm going to do. I'm just going to take Ts common. If I take out Ts common, it will look like this: 1 plus delta T by Ts whole raised to 4. The reason why I did this by taking out Ts common is because this looks like a binomial form. 1 plus x raised to n, 1 plus x raised to n. This basically will help me do an binomial approximation in the next step. Okay, I'll just put it over here, mc dt by dt. Now let's do this, E sigma A, and then if I expand this, 1 plus x raised to n, 1 plus x raised to n binomial approximation says it will be nothing but 1 plus nx, 1 plus nx. So this will become 1 plus delta T by, oh sorry, this was delta T like this, capital T, that T stands for temperature. Okay, so Ts but into 4 minus Ts raised to 4. This is the same thing. Now Ts and Ts, okay, I think when I took this Ts out, there will be Ts raised to 4 actually, because I took Ts and that 4 was also there. So Ts raised to 4 was actually out. Think about it. This Ts raised to 4 and this Ts raised to 4 will cancel out each other. So I am just left with E sigma A. I have Ts raised to 4. This is Ts raised to 4. And into delta T divided by Ts. This Ts raised to 4, this Ts raised to 4 has gone out. And here I have mc dt by dt. Next step, observe dt by dt will be, take this mc here, you will get E sigma A divided by m and c comes down, T raised to 4 Ts. One of the Ts will get cancelled, so I will have Ts cube, and what is remaining is just delta T. What is remaining is just delta T. Now there is one small catch over here. This is net heat lost, so the temperature is actually going to reduce. It's not going to increase, it's going to reduce. So the derivative will actually be negative. So everywhere just put a minus sign over here. Just put a minus sign because the temperature is reducing. So I'll just get a minus sign over here. So I will get dt by dt will be minus E sigma A mc Ts raised to 3. It's all a constant. So I'll just put a constant into delta T. This is called as the Newton's law of cooling. This is a derivation of Newton's law of cooling. This is a derivation of Newton's law of cooling. So what is this term? What is that term? Let me repeat. This term over here, dt by dt, is called as the rate of cooling. Rate of cooling. It's always in Kelvin per second, degree Celsius per minute, Kelvin per hour, whatever you want to keep. It's always temperature per unit time. That's called as the rate of cooling. This delta T is the difference of body temperature or the excess temperature, body temperature with surrounding. And why is this minus sign? This minus sign is there because it is cooling. That's why the Newton's law of cooling. That's all. So very, very important law, and this is the derivation for this. I hope this is fine. And I have put this up on the screen for you. dt by dt is minus k, difference of the temperature, and that's why the graph will come out to be like this. Initially it is very quick, later on it takes long time. Observe this graph very carefully over here. I'll just put it up for you. Initially, to change the temperature from here to here, just imagine I will only take probably this much time. Okay, to change the temperature by 2 squares, I'll probably need only this much time. Okay, let's say I call it T1. Now, next, to change the temperature by 2 blocks, that is from here to here, look at this. I might take some more time over here. Okay, so probably something like this. And for that next 2 blocks, observe this, it is taking more time. For the next 2 blocks, it will take even more time. I hope you can see the time taken increases. The time taken increases as you proceed. So what it means is the rate at which it cools slows down as the difference of the temperature reduces. So when there is less difference between the body's temperature and the surrounding temperature, it will cool down little bit slowly. Initially, difference between body temperature and the surrounding temperature is large, so it will cool very faster. I hope this is clear. So Kamal Raj, so in the binomial step, what just happens is basically when you have a term like 1 plus delta t by ts raised to 4, this is of the form 1 plus x whole raised to n is nothing but 1 plus nx. This is called as your binomial approximation. So when you have this term is very small because this number is very small. So when you expand it, it becomes 1 plus 4 into delta t by ts. That's how it comes. Is that okay? So that's what I had written down over there also. If you go back over here, that's what I've done. 1 plus delta t by ts is 1 plus 4 times delta t by ts. Okay, this is the binomial approximation step. Good. Good to go. Shall we solve 2 questions? Right? All right. 120 by 300 full test I got. Is it good or bad? It's not good. Okay. Oh yes, Kamal Raj. Yes, it is. That 4 is there. That 4 is there here. So that 4 is there here. Okay. I just put it up over here. 1 plus nx, 1 plus xn. It's the same thing. By the way, I don't know how many of you know this. Newton's law of cooling is also used in crime scenes to check if how much time has elapsed from the time the body was there or the person was dead. You know the surrounding temperature, you know the normal body temperature, so you know the difference. If you plot it graphically, you will get how much time was elapsed right from the time the person died. Yeah, that's how it is. GSK Telugu, you should get at least 200. Here is the question in front of you. There is a sphere, a cube and a thin plate, all made of the same material, having the same mass and are initially heated to a temperature of 1000. Which one of this will cool first? Which one of this will cool first? Very interesting question. Sphere is there, cube is there, plate is there, same material, same mass. If the mass is same, material is same, think about it. Think about it. Mass and density are same. That means volume is same. But shape is different. And the shape, if it is different, obviously the area which is there will be different. Who will have the highest area? Who will have the lowest area? Obviously, sphere has the area which is minimum, and the plate, when you make it as a plate, the area is going to be maximum. So it will be one of them only, extremities. Now why am I talking about area is because if you go back to the derivation, you will see this constant. You will see this is rate of cooling. Rate of cooling is negative constant into delta T. This constant decides how quickly the rate of cooling is. Apart from delta T, the constant decides. And do you see this constant has E sigma A MC Ts raised to Q 3. Do you see this constant? Okay, this constant has area in the top. That means when I write the equation of dt by dt, which is minus constant into delta T, this constant is directly proportional to the area. So more the area, more fast is the cooling. That means which one of this will cool first? So faster cooling will be there for larger area. And who has the largest area? The plate, and hence plate will be the answer. Yep, that's it. I hope this is clear. Perfecto. Moving ahead to the next question. Okay. A body cools from 50 to 49.9 in 5 seconds. How much time will it take to cool from 40 to 39.9? Assuming the surrounding temperature is 30, Newton's law of cooling is valid. Very interesting question. Let's see. First of all, what I will understand is that from 50 degree Celsius to 49.9 degrees Celsius, it has taken 5 seconds. And all this while, the surrounding temperature was how much? 30 degrees Celsius. If I use Newton's law of cooling, which says dt by dt is equal to minus k into the body's temperature minus the surrounding temperature, think what will I get? dt by dt is how much is the change in temperature per unit time. The change in temperature was 0.1 degree Celsius upon time taken was 5 seconds. Time taken was 5 seconds is equal to minus k. Body's temperature. Should I take it as 50 or should I take it as 49.9? Should I take it as 50 or should I take it as 49.9? They are very close to each other. So just write it for simplicity, for calculation's sake, just write it as 50. Minus surrounding temperature. What was the surrounding temperature? It was 30. This is the first case. Okay, this is the first case. Second time, when the temperature comes down from 40 degrees Celsius to 39.9 degrees Celsius, the question is how much time does it take? This time also the surrounding temperature was 30 degrees Celsius. Just write the same equation. 40 to 39.9, how much is the change in temperature? It's 0.1. How much time? I don't know. Is equal to minus k into body temperature. Should I take it as 40 or 39.9? Take it as 40. Will make the calculations easy. Actually speaking, you should take the average, which will be 39.95, but it's okay. It's nearly the same. So 40 minus surrounding temperature is nothing but 30. Obviously, what's the next step? Divide both of them and see what do you get. So divide both of them. So when you divide both of them, so 0.1 divided by 5 upon 0.1 divided by t is equal to minus k cancels. So 50 minus 30 upon 40 minus 30. So 0.1 cancels. So it will become t divided by 5 is equal to 50 minus 30, that's 20, 40 minus 30 is 10, 0, 0 cancels. So t will be equal to 2 5s are 10 seconds. Is that there? Yep. 10 seconds is the answer. Very good, Abhinav. So this is how you use Newton's law of cooling. It will be mentioned, and these questions are very common in JEE Mains, even in JEE Advanced. So you should have a good knowledge of how these questions are solved, and especially this derivation which I just did is very, very important. Okay, so that's why I did it in front of you. All right, so I kept some homework questions, I believe, after this. Yep. Coefficients of absorption, reflection. So based on the first part of the chapter, then you have, another question on radiation over here. Okay, on Stephen Boltzmann law, and then another question, very interesting, based on geometry. So let's see how many of you can do that. And the fourth question based on Newton's law of cooling. Post all the answers in the comment section. That way you will be inclined towards solving it regularly. Plus it will brush up whatever we have studied in today's class. And let me tell you, this is our usual price chart for the 11th standard course. This is 1350 rupees for 15 days, and you get additional 15-day worth of course. Using my coupon code SHHPRO, you get 10% off. It's a very interesting offer because you hardly have to pay anything. But I would suggest you wait for one day and join the courses on Monday. See, if I wanted, I could have told you, just join it today. See, if you go to the description box as well, you will see it. It's right over here when you're watching my videos. Okay, let's just go to this video out here. All right, go down, and in this you will see the JEE 2-year course over here. This is 11th standard plus 12th standard course. 11th standard revision done before your March, and 12th standard long-term batch where even I will be there, KVPY preparation, other exam preparation, all till the end, JEE 2023 last exam, including CBSE revision, CBSE mock tests, including your JEE tests, JEE assignments, booklets, everything is provided. And the usual price is 1350 for 15 days plus 15 days offer using my coupon code. But on Monday, you will get even more off and you will get the course for 750 rupees. So I would suggest go ahead, you make use of the Republic Day offer, which starts on Monday, and avail this at 750 rupees for 1 month, which is a big deal. And even if you go for the other packages, okay, Classic and Plus, you get that offers. And the only difference in Classic, Lite and Plus, which is very important for you to know, is that the doubt solving is there on the mobile app in the Classic version. And in the Plus version, you will get additional personal mentorship, which is many people require that. They want some guidance, some kind of support apart from the teacher support that you get. So you can try that out as well. And even the highest package cost for the course till JEE 2023 is hardly 97,199, which is half or 1/3 the price of your regular coaching. So I would request you to try it out, make use of the offers that we are giving you, and join the Telegram channel. It's all there over here. This is a Telegram channel link as a new Telegram. Make sure you have joined it. Okay, so that's the information I had for all of you. Very important. I hope I'll see you very soon. Next lecture will be on thermodynamics. We'll be starting on Monday and we'll complete thermo next week. All right, cool. Thank you very much. Take care. Have a great time and study well, and make sure you post the answers in the comments section below. And thank you for liking. Thank you for hitting the subscribe button. Bye bye. Hasta la vista. Take care.